So today is about figuring out how much is the change in energy transfer, what does it depend on. FRET has been around basically since 1967. And why it's useful is basically the reason I just gave. The fact that it depends on an order to the sixth distance between the 2 points, one labeled with a donor, one labeled with an acceptor, is actually critically important. So because it depends on, well, order to the -6, the energy transfer is very large when it's close and rapidly decreases with distance. It's also a very convenient technique. As you will find, you can relatively easily make a measurement. How easy it is depends on, I guess, how well you do. It's also useful because you can measure ensemble FRET. That is, you have a bunch of donors and acceptors together, and that's what we call ensemble FRET. But you can also do it at the single molecule level, which is, I guess, something that's of tremendous interest to me, basically because I co-invented it, and because when you can measure single molecule FRET, you can have a whole ensemble of molecules, protein 1, 2, 3, which are seemingly all the same. But in fact, you will find that in sometimes it's fairly close, and sometimes it's medium amount, sometimes it's even far. And it turns out by knowing what that distribution is can tell you a lot of information about it. Okay, so this is basically just a reminder of what FRET is. And again, it's where you have two molecules. One is called a donor, one is called an acceptor. If they're far apart, that is much greater than R0, the characteristic distance, then you get essentially no energy transfer. And this green dye, the donor, you will go and excite it, and it'll emit, won't even know about the red dye. However, if you bring them closer together, you have a red dye and a green dye. When you go and excite the green dye, it doesn't fluoresce. Instead, it transfers its energy over to the red dye, and the red fluoresces. So again, you can tell the distance between them by the amount of red and green. And that's quite useful because you have a protein over here, maybe as a function of ligand, it will crunch up. So there you get an intramolecular FRET, no FRET, FRET. Or you can get an intermolecular FRET, that is, by itself, you see nothing, and then two of them come together, and you see FRET. OK. And this is what you really need to understand. And we did talk about it a little bit in the last lecture. Again, you have a green and a red. Or in general, you have that the acceptor is a little bit red-shifted. And we'll understand exactly why that is. So you have a donor, which let's say emits in green. So when you excite it in blue, it emits in green because there's a little what's called Stokes shift in the donor. It takes some energy, loses a little bit of that energy, gets up here, and then it either fluoresces, or it can come down non-radiatively, that is, it just loses the energy via heat. Or if this guy, the acceptor, is around, it can transfer the energy, and this gives up energy over here. And while it gives up energy to the acceptor, therefore it loses energy. So for example, looking right over here, what do you think the relationship between the emission of the acceptor and, I don't know, let's say the emission, donor. The emission of the donor and the emission of the acceptor is? Or between the donor's emission and the acceptor's absorption? What do you think it is, based on this diagram and this diagram? Who can tell me? Okay, since you can't tell me, why don't you try to figure it out with your partner? Go and talk for a couple of minutes, and
what do you think it releases issue?
Okay. Let me clarify exactly what I'm asking. The donor, this molecule, has some wavelengths that it does absorbing in, and some wavelengths that it does emission in, donor, and does some emission. And the acceptor does some absorption here and some emission here. So what's the relationship? In order for this to transfer energy from the donor to the acceptor, what is the relationship between these various energy levels? Is the energy levels of the donor bigger than the acceptor, smaller than the acceptor? What about for energy for the energy of fluorescing, and first the energy of absorption. Where is that here? And then what about the energy that it actually fluoresces at? And how does that relate to the absorbance of the acceptor and the emission of the acceptor? Was that any clearer? Okay, at least for some people it clarified it. Does any? No?
So are you asking, like, does it change in energy, or?
No. Let's say, okay, well, we'll do this together for a little bit. Okay, got another question.
So one thing that you said last week was that that we were able to figure out that the acceptor wasn't simply absorbing the light emitted by the donor, because the light emitted by the donor was at a lower energy than that was required for the acceptor to reach the higher energy levels.
That's not quite true, but you're thinking along the right way. But okay, let's go and think about it. Okay, let's say this donor here. What is its wavelength of absorption? Which value is this over here? What's that? I'm sorry, couldn't. Yes, it's the blue one. Careful. This is actually. You're right. It's a relatively small wavelength, large energy to bring it from here up to here. Okay, that's why it absorbs in blue. And then we know that it fluoresces in green. Which energy levels is that? Okay, you would doing such a great job. Just green. It's fluorescing over here because it takes some of the blue light, absorbs it, loses a little bit by non-radiative processes, goes down here, and then decides to fluoresce. Or sometimes it just decides to to go down via the emission of heat. Yes?
But when it's transferring, you don't really need to go through that process of...
Ah, okay. It gets knocked up here in about a femtosecond, transfers over here in a few picoseconds, then it stays up here for like a nanosecond, and then either comes down, or if there is some guy nearby at the right energy levels, that acceptor can take that energy. It is not, it turns out, the emission of a photon here, which then gets absorbed by a photon. It is not. And we can actually go through what the energy transfer mechanism is. But it's not simply emission and reabsorption. It's the fact that this acceptor is very nearby. It's in what's called the near field. Oh, apparently I'm raising trouble there. Okay.
So when we were talking yesterday about fluorescence only being possible in molecules where there can be resonance in the electron within the molecule, here what would happen is that the two molecules become so close together that this resonance becomes possible between the two molecules?
No, actually, it turns out that in order for the two molecules to actually, if they're, well, they are resonant with each other, but it turns out that they're resonant to the point where this guy and this guy, the donor and acceptor, do not change their wavelength, their absorption, or their emission properties. It turns out that you actually do have that if the molecules actually come even closer together. So in this case, that you don't have that. Yes?
So what's the time scale for the transfer of energy?
The time scale for the transfer of the energy is just like this, on the order of a nanosecond, because it actually can compete with this guy going down here. It turns out that if it was exactly equal, then you'd get like half. You know, half would go down, half would transfer. If it's even faster, more transfers. If it's a little bit slower, more fluoresces.
So is the transfer essentially lossless?
Yes.
Okay.
Yes. Okay, so what happens is you have an acceptor which has some energy which can take this energy over here. Still, it's a green. It's not a photon, but you can call it a virtual photon. You have this virtual photon coming down here, and it causes it to be raised up here. So in order for the acceptor to do a good job accepting energy, it better have an absorption region right where the donor has fluorescence emission. Yes? That makes sense. Okay. And so the donor's fluorescence wavelengths should overlap the acceptor's absorption. And it's true. And then this guy, remember, it gets excited. Now it's excited, so it will transfer within a few picoseconds and come down to this state, and then fluoresce, or not fluoresce. Depends on how good of a fluorescer is. Yes?
So the acceptor can't accept the blue light? Like it can't absorb the blue light?
In general, it can't. Actually, it turns out that in reality, to a certain extent, when you excite the donor, the acceptor also absorbs some. And that's actually a royal pain in the butt. You have to go and subtract that off, and we'll talk about how to do that.
And also, are the energy scales scaled
Oh, yeah.
on that thing?
Oh, yeah.
So wouldn't you say that the energy that goes down, the green one,
Yeah.
it's technically until the 0.4 the blue one, right? Like the energy is actually the whole thing. Like from the top of the green
Well,
one, from the tail of the green one to the tail of the blue one, there will be the whole energy, right?
This is the whole energy of absorbance.
Yeah.
This is the whole energy of the emission. Of course, when it gets down to here, that's some higher vibrational state of the ground state, and so it very rapidly loses
So why
effect.
does the energy transfer just until the point of the green light and not the whole thing, the whole energy that it has?
Well, in fact, there's a bunch of states where when this guy fluoresces, it fluoresces with this wavelength. Also, it fluoresces with about that wavelength. And in fact, as if the acceptor has a state that can absorb there, it will fluoresce there as it will absorb there as well. In fact, let me show you a graph of that. Okay, and so what we found is the distance between the donor and the acceptor over here, it looks like 1 over 1 plus r to the 6th with a normalization parameter. And that normalization parameter we call r naught, which is the distance at which 50% of the energy is transferred. And so when you have the donor and acceptor nearby, a lot of the time the donor gets over here, and its efficiency of transfer is very high, very high. So that means very little of it is going to go down via fluorescence. So that's going to be small, where the acceptor will be really big in fluorescence, so that will be very tall. When you're at R naught, they'll be about 50-50, and when it's really far, the donor doesn't even hardly know about the acceptor. So the donor is doing its normal emission, and the acceptor theoretically is 0. In reality, you actually do get some fluorescence, because when you're in the blue light, you inadvertently shine some absorption of the acceptor. And so that's non-zero. So you have to figure out what that is. Yes?
In the graph, what does E represent? Does it represent energy transferred or energy emitted?
This is, E is the efficiency of energy transfer.
Okay.
So E is 1, or multiplied by 100 is 100%, and here E is 0, namely none of the light. And when E is 0.5, then the energy transfer efficiency is 50%. Yeah, thank you for clarifying that. Okay? And also, there'll be a difference between the lifetime of the donor, because the question back there was, if this has a lifetime of, let's say, 2 nanoseconds, and it has, let's say, 50% energy transfer. So this process takes up, essentially, is about a nanosecond. So this is left with a nanosecond. So the donor lifetime, it's faster. And it's faster. When the donor, the lifetime, if the acceptor is far away, it is just basically the donor's lifetime. In this case, it's about 2 nanoseconds. Let me give you some examples. What is the energy transfer? I always have to remind myself, it goes as 1 over, R naught over R to the 6, or R over R naught to the 6. I can never remember. I mean, I've been doing this for, God, I don't know, 20, 30 years. God. I'm old. And I still can't remember. So how do I figure it out? Each time I have to write it down.
The one that doesn't go over 1.
Okay. So which one doesn't go over 1?
All won't go over 1.
All right.
Just take the limit as the drug goes to the.
Right. Exactly. Just take the limit. Let something go to 0 and go to infinity. This is a general rule. So R can vary. R naught is a constant, depending on, well, we'll find out actually what it depends on. So this is a constant. So if R goes to infinity, this goes to 0. So that's 1 over 1. So the energy transfer is 1 at infinitely far apart? No, that doesn't make sense. Let's say over here. If R goes to infinity, infinity over a constant number is equal to what? Come on, you know. Infinity. So 1 over 1 plus infinity, that's infinity. 1 over infinity is 0. So E goes to 0 when they're very far apart. That makes sense. And if R equals 0, well, this is 1 over 1. The energy transfer becomes infinite. Or, I'm sorry, the energy transfer efficiency becomes 1. Okay? So you can take the limit. Okay. Now remember what I said about the donor emission and the acceptor absorption. So this is commonly what you will see. This happens to be fluorescein as a donor and rhodamine as an acceptor. Here's the absorbance, and there is the emission. Notice here it isn't just exactly only one wavelength that it is emitting, and the acceptor is one wavelength which is absorbing, but it's over a range. So that's the emission, and here's the rhodamine absorbance. So actually, what it will really count is the overlap between the donor emission and the acceptor absorption. The bigger that number is, the more efficient it is, the higher R naught it should be. Because it can if R naught is bigger, meaning it can transfer energy even if things are fairly far apart. And then, of course, it emits. Okay, and what happens is the normal fluorescein fluorescence is, let's say, this big. But we said when it's undergoing energy transfer, it's giving up some of that energy and not emitting. So its emission will go down. So if you think of this semi-quantitatively, you can say, okay, how much is the emission initially with just a donor? Then you bring the acceptor in, and it'll undergo some emission. And so the amount, the energy transfer will be equal to what? Can we get now a quantitative description of what the energy transfer will be some function of the fluorescence of the donor and some function of the fluorescence of the donor in the presence of acceptor. So who can figure out exactly what this is? Because I'm about to give it to you. But you should be able to at least think about it. So why don't I hand it over to you? Then in a minute you can say, what exactly were you asking? And then we can do it again. And that's fine. Go ahead. So it's like, huh, what is he talking about?
What's going on?
Who's going to be the first to ask? Okay, so let me interrupt you. And so what am I asking? Let's say I have the donor let's say by itself, which is emitting. Let's say emitting with, or let's say I, with some intensity I of the donor. And then let's say we have the donor this time with an acceptor at some distance r away, and it has some emission of the donor, what we call D sub A. It's the emission of the donor in the presence of the acceptor. That's what this is, right? So now I want to know what the efficiency, I want some equation. The efficiency, what do you think that it looks like in terms of ID and IDA?
The ratio of the two.
The ratio of the two. Okay, now what we're going to do is we're going to take the limit, just as, is it Andrew? Is Andrew correct? Yeah, I got it. Just like Andrew said, we're going to take the limit with that, for example, he says the E. No, you want this? Okay, it's getting better. Well, okay, but in the limit where, let's say, R goes really far apart, is E going to 0 or going to 1, or, so tell me, take the limits and see, does that in fact have the right limits? Okay, I'll let you work again. No, yeah, the donor in the presence of acceptor. Careful, not quite. This should be, E should be dimensionless. E has units of none, either 1 or 0. If it's just ID minus IDA or vice versa, what units is that?
Or less.
So I mean, you're thinking right, but modify it slightly. ID is the intensity of just the donor. IDA is the intensity also just the donor, but in this case with the acceptor nearby. So ID sub A. Okay, and what units should it have? E is a dimensionless unit. E is 1, 100% energy transfer, or 0. It's a ratio. So if you want to come up with some equation, it better be unitless.
Like the whole thing?
What do you mean the whole thing? E, you're saying E equals something. What I've heard is IDA over ID. Okay, that's actually unitless. I've heard of IDA minus ID. That's not unitless. Okay, so the units have to make sense, but,
That over ID will be units.
huh? No,
IDA minus ID
Yeah,
over
I
ID.
think it's
Delta is the.
ID minus IDA over ID.
oh. Oh. So E is equal to what?
I sub D minus I sub dA divided by I sub B.
Which is equal to, what?
Regarding the limits, or,
No,
oh, delta I guess, delta ID?
well, what's ID over ID? You can all do higher math. 1, okay, good. 1 minus IDA over ID. Yeah?
Is the intensity proportional to the number of photons, or is it?
Yes, it is. Okay, so you say that it looks like this. Well, let's see, does it have the right units? This is unitless and this is unitless. That's good. Does it have the right sort of distance dependence? Or can it be greater or less than 1? What about that? Is IDA bigger or smaller than ID? Smaller. So this number is less than 1, or most 1. So it's going from 0 up to 1. So that's looking good. What's your name?
Charles.
Charles. Everybody like it? All right. Good. That's exactly correct. Well, okay. Yeah, you'll see it written up here in a little bit. So that's right. Okay. Interestingly enough, so we figured out basically from the donor fluorescence what the energy transfer is. This is from the intensity. What about from the lifetime? You have a similar. What about from the lifetime? What do you think it is that's from the donor lifetime? What do you think it is there? What kind of equation can we write? So E is going to be some function of the lifetime of the donor and the lifetime of the donor acceptor. So what do you think it is? Oh, okay. Okay.
So I don't really get why the lifetime would decrease if the donor is releasing less light. Why does the lifetime?
Okay, the lifetime decreases. Okay, this is my little analogy. Okay, who wants to be a volunteer? Okay, come on up. Yeah. It isn't that dramatic, really, but okay. Okay, so he's walking on the, like the 100th floor of some building, and he's blind. Okay, but he's kind of anxious, sort of. He's generally sort of moving around in a random way. Okay. And what he doesn't realize, okay. You can look for now, but I'll ask you to close your eyes again. what he doesn't realize is that the building is still under construction. So there are holes in the floor, and the holes are big enough for him to step and fall, okay? So the question is, how long will he live up there? Okay, so when he closes his eyes and he starts going around, and eventually, whoosh, there we go. And he falls down, okay? Let's say that he falls down. When he falls down, he emits a fluorophore. I mean, he emits, put it down. He emits a photon. Raise it up. There we go. Okay? So his lifetime call it that K radiative. And, well, 1 over K radiative would be tau radiative. So on average, he will live about tau, or tau r, right? Okay, stand up. Now he's standing there, eyes covered,
That's not me.
eyes covered.
Okay.
And he's feeling the same kind of thing and jiggling around and going on. And now there's actually 2 holes in the floor, which he can both fall through. And one, he emits a photon, and the other, he just falls dead. Okay? Whoa! And no, it doesn't go, whoa, boom! Okay. Okay, you can get up.
All right.
No.
Oh, no,
I didn't say.
Okay.
And there's the K, or it's K heat. And so now tau is equal to 1 over K radiation plus K heat. And in fact, it does have most fluorophores, when you go up, and it doesn't come down automatically emitting a photon. Sometimes it emits just heat, okay? So in fact, the tau will be this.
And so since out of like two scenarios, there's just like less chance that it's going to radiate, it's going to take longer to radiate.
Exactly. It won't take longer. It's the same time, but there's another competing process that also can maybe take less time. And so the overall time of your lifetime is going to be shorter if there's a lot of heat. Okay, now, now, what do we do? You cover his eyes.
Oh.
Okay. Jaya says, well, this is bad. Okay, and now he's going around, and he almost falls into the radiative hole, but he doesn't. Almost falls into the non-radiative hole, but then he falls into another one called the energy transfer hole. Okay, and he goes down, whoops, and he goes and falls. Okay, but on his way down, there's actually a seesaw. Okay, and he goes down, and he hits the seesaw, and what's on the other end is his friend. His friend is named the acceptor. The acceptor, whoosh, gets knocked all back up exactly to the original height he was. Okay? Okay.
Or the acceptor.
No, the acceptor. But it's okay. You've done your acting. Okay. So. Okay, you can sit down. Okay, let's give him a. And now there's another another way that it can go down. And so K is the sum of all of these. And so K, we said for the donor was just this, but when we have K for the acceptor, the donor now in the presence of acceptor, is equal to 1 over K radiative plus K heat plus K fret. So in fact, there will be a decrease in the donor's lifetime in the presence of the acceptor, because what the acceptor does is essentially he makes a little hole. And actually, it's not necessarily a little hole. It's maybe a huge hole. And a huge hole is really likely to go down there rather than just to give up heat or to give up a photon. OK? So here, what we have, so what do we think the energy transfer, the efficiency, is equal to within tau d and tau dA? What do you think? Tau d and tau d sub a. Again, should be exactly like before in that it must be dimensionless. The lifetime must go to 0 to maximum of tau d, etc. So Charles is, what's the expression? But biting the, no. When a dog is, trying to, come on. No.
A barking dog does not bite or something.
Charles is not a dog. Okay. Okay, Charles?
Well, I think it would be the same equation, 1 minus tau dA over tau d.
Oh. And that's exactly right. Okay, let's give Charles another big round of applause. Man, his ego is going to become really big after. Okay, so you can actually measure the energy transfer either by a decrease in the donor intensity in the presence of acceptor, or you can measure a decrease in the donor's lifetime in the presence of acceptor. And that's good. So the only thing that we, yes?
Yeah, so this works if the efficiency of, or if basically the transfer of energy to the acceptor is becomes greater given the short enough distance than the loss of energy through heat or fluorescence. But are there cases where even at very, very close distances that transfer is just still more difficult?
Yes, it basically is a function of what R naught is, how efficient the energy transfer is at a particular distance. And if R naught is really big, the energy transfer is really efficient even out to far distances. Where if the energy transfer is really small, unless you bring it in really close, then you're going to have difficulty doing much energy transfer at all, unless you're incredibly close. Another way of saying that, or a slightly different way, is saying if the quantum yield of the donor is very low, it's going to be lousy not only at giving up a photon, because it's mostly going to heat, but for that reason, it's also really lousy as a FRET donor. And so in general, you want to pick ones, fluorophores, that have a reasonably high quantum yield. That is, they're good fluorophores.
So is fluorophores that are used, is it based off of their quantum yield, or there are not?
It turns out, well, hopefully we'll get to it, but they're directly related to each other. Okay. So,
Could you explain that one? Those look at ratio, I didn't
this, okay, this says that what you can do is you can take the lifetime of the donor, the lifetime of the donor, either like in the absence of acceptor, or if the acceptor is really far away. In that case, it'll have lifetime we call tau sub d. Okay? Then what we do is we can measure the lifetime of the donor when the acceptor is nearby, and it can be doing a fair amount of fret. That's what we call tau d. Tau dA. And the physically, the E, how we actually measure E, the energy transfer, is 1 minus this ratio of the two. In many ways, very similar to we look at the intensity of the donor in the presence of acceptor divided by the intensity of the donor, and 1 minus that.
So why is it two on the same? Why is the two ratio not the same?
Why are the two ratios?
Yes, why they are the same?
There's two ways to measure it. You're going to do that in the lab.
Yeah, this in turn is, this is the intensity, not as a function of time, just the steady state intensity. Intensity here is a lot, intensity over here is less. Or you can do it as a function of time. You come in with a really short laser and you pulse it, and then it'll drop down in a certain lifetime. Or, as we talked about in last class, you can also measure the lifetime via a frequency modulation.
Is this 50 angstrom universal or just for this example?
It is not universal. 50 angstroms is a fairly large R naught. Typically, it goes down to about 20 angstroms and goes up to 70 or 80 angstroms. That's quite unusual.
So it depends on the donor and receptor you choose.
Exactly. It depends on the donor and acceptor. And in particular, it depends on how much emission, how much room there is between the fluorescence, the emission of the fluorescence, and the absorption of the acceptor. So what you do is actually you can quantitatively compare this by essentially just integrating this area, and then you take other spectra. For example, here, oh well, this is fluorescein tetramethylrhodamine, so that's not different. But in your case, I think you'll have dyes called CY3 and CY5, and they'll have a different absorption, so that their R naught is somewhat different. Okay? Now, the one thing that we haven't talked about yet is we've talked about measuring the energy transfer looking at the donor's emission. We haven't talked about measuring the energy transfer by looking at the sensitized emission of the acceptor. That is, the acceptor will have a certain amount of fluorescence. Actually, it will have a certain amount of fluorescence, because when you come in with the blue light and you mean to excite only the donor, you inadvertently excite the acceptor. So it has a certain amount. However, fret will cause another increase in the amount of energy. So, for example, if the donor and acceptor are really far apart, so you assume that there's no fret over here, you get a little bit because you're inadvertently exciting the acceptor when you just mean to excite the donor. So that's 0. But then when you actually have some energy transfer, you bring this in, this guy goes way up. Yes?
If it was possible to provide an excitation light of a single wavelength, would it be possible to avoid that?
In general, the answer is no. The reason is, take a look at, this is the acceptor absorbance, and this is the donor absorbance. You know, ideally, you can use a really narrow wavelength, and you go here and you hit the donor's maximum, but actually there's still some absorbance of the acceptor. Okay, so you say, well, okay, let's move it a little bit that way. Well, if you went from here to over here, yes, you know, you'll maybe have a 20% decrease in the acceptor absorbance, but you actually have, you know, a 50% decrease in the donor's absorbance. So actually, it doesn't buy you anything. And if you say, well, let's not take a rhodomine, let's take another acceptor absorbance that, you know, the whole thing is shifted over there. Well, that's true. That buys you this better ratio of not having the acceptor absorbance. But it also, by having this out further, then the donor's emission and the acceptor absorbance decreases. And that says the integral here is decreasing, so your R naught is decreasing. So you lose that way. So it's a gain. Yes?
So if you could excite the acceptor, could the transfer of energy be reversed? Or go to the donor?
Oh. So here's the acceptor absorbance. In general, this is farther to the red and generally lower energy than the donor. So in fact, basically the answer is no, because in general, what you do is, you know, to cause this to fluoresce, you're hitting it here, which is then going into here, which is lower energy, and basically you're not getting uphill that way. So, yes.
So the graphs to the right of the donor acceptor, are they graphs of intensity or absorbance or emission?
This is, okay, a good point, is graphs of emission.
Emission.
I should have made that clear. I should have. Okay?
They'll be doing this lab for 2 weeks, so you can actually finish the acceptor part of it.
Okay.
I think
So,
next week.
so she's the sensible one saying, oh, shut up already. I'm just like,
No, I mean,
yeah.
It's just,
It's,
that's more than
it-
two slides.
it's kind of like my wife. It's like, you've had a good time now. Okay, I'm going to let you go. Just hold on. We have another question, and we have a chance for you to write some little bit. Yes, Andrew.
There's an overlap of buildings in addition to, would it be possible for two molecules of the same sort to have fret with each other?
That's called homofret, where you have fluorescence donor and a fluorescein donor and a fluorescein acceptor. And they can, in fact, have energy transfer between themselves. And you can actually measure that, though how you do it is a little trickier because they're the same donor and an acceptor. So that's a very good, interesting